Okay, so we're going to talk a little more about definition of derivative, and let's just go with what we started last day just to jog your memory of where we were. So the limit process that we were using is the limit as delta x goes to 0, and it's the function at x plus delta x minus the function at x. And this is one of those limits which is a 0 over 0 case. So it's something, as we say, you have to do a little more digging to actually find what the real limit is. So do you remember what the strategy was here for getting rid of our 0 over 0? Going to do some creative multiplication. What do you? Yeah, it's that rationalizing the denominator. Well, we're multiplying by the conjugate to do it. So it'll look like this when we multiply through. And we don't want to actually distribute it. We're just going to use the pattern to give me x plus delta x minus x. And on the bottom, I'm going to leave it factored. Usually, if you're getting used to doing these limits, it's usually to your advantage to leave them factored. So we've got the limit as delta x goes to 0. Collecting my like terms, I have a delta x on top, delta x on the bottom, and root x plus delta x plus root x. So that removes the 0 over 0 problem I started with. And what I'm left with is 1 over root x plus delta x plus root x. So if this one goes to 0, that's not a problem. All that's going to happen then is I'm going to end up with 2 root x's on the bottom. Now, we will have a chance to talk very shortly about how we can get through this process quicker. Some of you might already be picking up some patterns in this. But for now, anyways, we're going to take a look and see what we can come up with using the limit process. And this one is asking us to find the equation of the tangent that's parallel to this line. So when you look at that line, there's something very, very key to helping us solve the problem. So when you see that line, and you hear the word parallel, what should come to mind? Slope should come to mind, right? Because if you want two things to be parallel, they have to have the same slope. So what is the slope then that I'm looking for? 1/4. So it's the one here. If it's parallel to that line, it's got to be the same slope of 1/4. So that means I want 1 over 2 root x to be the same as that line, which is 1/4. Now we could go and solve this in a complicated way, but can you tell me just by looking at it? Yeah, because once I square root it, I get 2, then it'll be 2 times 2 on the bottom is 4. So x equals 4, that's where the tangent line is parallel to 1/4 x minus 2. So if I want to know what's the equation, this was the one that we worked with last day. So you go y minus y1 is mx minus x1. And that'll give us, in this example, at x equals 4, if I put it into the graph, this is the function. It's y equals 2. We just said the slope has to be 1/4 to be parallel, and the point for x is at 4. So this would be the equation of a line that is parallel to 1/4 x minus 2 and also passes is tangent to the graph square root of x. So here's what we were actually doing in that picture. I'm going to put those equations into this graph so you can see what we were actually doing. I'll tell you, if you're not already doing this, you should try and make sense of what we're doing with a picture. So if you are having troubles making sense of it, see if you can draw the picture of what's going on. because the visual side of it sometimes is very helpful for you to see what the process we just did involves. So we have 1/4 x minus 2. There's the line. I guess I'll zoom out a little bit here so we can... something like that. And I have the graphs for the square root. And then the equation that we found was y minus 2 is 1/4 x minus 4. So there's the two parallel lines, one of which is tangent to the graph. So the one that we solved here, this is the one who just skims the graph right there at x equals 4 and y equals 2, right where the crosshairs is. That's the tangent line we just solved for. So I know it's a lot to digest, but this is the process that we did, and try and give you a visual sense for what we did. I can probably even give you a better picture here. We probably don't need to go higher than that. Okay. So we have another definition that can help us find these problems. This is the alternate form for the definition of derivative. And it's convenient sometimes. I'll show you so we can compare them, and then you can see which one you like better. But we've just done the definition that we did the other day. Now we can try this alternate form just to see if that would be any better. So here's our first one, right? And if I was to compare, let's do the limit process. The limit as x goes to c. And this time I'm evaluating it at two different points. So I've got 2x squared minus 3x plus 5. This is the function at x minus the function at c. This won't get us anything new, right? This isn't going to give us any new information we couldn't have found before. But one thing it is going to do is, you'll notice we don't have to expand, right? Before, when it was x plus delta x, we had to expand everything out. Now we don't. So the trick here is going to be, how do we remove this discontinuity? The only way we're going to be able to remove that is if we're able to factor it out. Okay? So let's just see what happens here when we collect some like terms. The first thing is, things still will simplify, so that 5 is going to be gone. It's in both pieces, so when I subtract them, it'll disappear. And I have 2x squared minus 3x minus 2c squared minus, sorry, that'll be plus 3c then, all over x minus c. So everybody's getting these x's and c's in their... each piece either has a multiplication by x or by c. But now we have to think of a way to rearrange this so we can factor out that problem, right? That x minus c is still giving us a problem. Okay. So let me just try and readjust some of this limit for you. Oh, yes, sorry, it's a 3c. So I'm going to do the factoring part of this with you. It's takes a little bit of practice to see that kind of factoring at this level, but I have x squared minus c squared, and the other one I'm going to write as minus 3 times x minus c. And this one here is the difference of squares pattern, which is x plus c times x minus c. So I'll get limit as x goes to c. This will be 2x plus c, x minus c, minus 3, x minus c. And now I can take them out because they're in all three pieces. So that's gone, and that's gone. I've divided the x minus c out of all those pieces. And it leaves me with the limit as x goes to c of 2x plus c minus 3. So what's going to happen as x goes to c? It just becomes a c, and there's no more division by 0, so this would be 2c plus c minus 3. So this will become 4c's minus 3. So that's the equation for the derivative. You give me a point for c, I can give you the equation of the derivative for that. So of course you have to weigh these things out. You might like the other definition better. It might be more convenient to use. There's no time when you'll be required to do one of the two definitions, but it gives you an alternative if you know that it's going to make life easier. I think the next example might be a better example of where it fits in. So this time I have x minus 2. I'm going to take away at c minus 2. And now I'm going to multiply through by same techniques we learned in limits. So it'll be root x minus 2 plus root c minus 2. And we have the whole thing on the bottom here, x minus 2 plus c minus 2. And this one actually comes out pretty quickly, because now when I subtract them, I'm going to have x minus 2 take away c minus 2. And on the bottom, x minus c, and I'm running out of space here. I'm going to move this over. I took too much. One more time. It's not cooperating with me. I'll just, I need some more room here. Okay, so we have the limit as x goes to c and on the bottom so those 2's are going to disappear, and I end up with this limit. This will be x minus c over x minus c x minus 2 plus c minus 2. So now I've removed my 0 over 0, and I can come up with the limit. As x goes to c, this is just going to be 1 over c minus 2 plus c minus 2. So that's 1 over 2 root c minus 2, since there's 2 of them. So that's the last one, I suppose, that we'll do for the derivative as far as using a definition. You should know I'm not super concerned about your proficiency at this, because as I said, we are going to discuss better techniques. However, you do need to know this definition. You can't just throw it away and forget about it. It does come back. For example, I'll just show you something that could show up as a question on your AP exam. They usually do things like this. Sorry. And that should be 0. So you might see something like this, and it's been a while since you've done it, but if you recognize what's happening here, this is the definition of derivative as, sorry, let me just see here, and that should have been, sometimes it's not the greatest to do it off the top of your head, but this would be like the question you'd be given, which you don't have a technique for, other than maybe you could use your sign addition identity. But what you could convince yourself of is this is the same thing as the limit as x goes to 0 of sine pi plus x minus the sine of pi. Because the sine of pi is 0, I'm not actually subtracting anything. And now the limit looks like the definition of derivative. This is equal to the derivative of sine at pi. So even though we'll have better techniques, it doesn't mean you can get away with forgetting that this part was here. And of course, we will practice this specifically, but that's more so you do need to recognize it. You don't need to be proficient like we've been doing here. All right, so now we have to talk a little bit about differentiation. And again, it helps if you think about it as a limit to answer some of these questions. So since we know it's a derivative, we can approach from either side, and we should be able to tell, you should be able to tell me, does the derivative of this function exist at x equals to 2? So this is the graph. It's an absolute value graph, so it's going to look like this. And I'm asking you to tell me, does the derivative equal to, does it exist at x equals 2? What do you think? So this is a good time to recap. What's a derivative do for us again? It's a tangent line. Yeah, and we're not going to use it in this example, but what else can a derivative do for us? Yes, it's a slope, and we're thinking of that as a rate of change. So the two things that you always have to keep at the front of your mind, that derivative is finding a tangent line for us, the slope of the tangent line, and it's also finding a rate of change. In this case, the slope is what we're talking about. So can you describe for me what the slope of the tangent line would look like? Like, I mean, how about this? Does that work? Okay, how about this? How about this? What do you think? Is there a tangent line at that point? Well, the derivative is very specific. What it's saying is, what's the limit as I approach so we'll say we'll go from the right side. So as I approach from the right side of the graph, this is what I'm doing. I'm going this way. So the tangent line, if all you did was look at the right side, that's the tangent line there. That has a slope of 1. The slope of the line as I approach from the right-hand side is 1. However, if I do the same thing, let's, that's fine. From the left, what's the tangent line this time? It's -1, because it's coming from the left side. So does that limit exist? We haven't forgotten limits that quickly, right? Does that limit exist? How come it doesn't exist? It's different. There's a jump discontinuity. So from one side to the other, those limits don't meet. The limit does not exist. If that limit does not exist, there's no derivative there. All right, cube root. I don't know if you know the cube root graph that well, but do you think there's going to be any problems when we look for a slope on the cube root? So that's the cube root graph. And here's a picture. Maybe I'll zoom in a bit more. So what do you think? Will there be any problems here if we're talking about the derivative? I'm not asking you about this graph. This graph is fine. It's defined everywhere. But what about the derivative? And remember, when I say derivative, that is a word which describes a lot of things, but the two that should always come to the front of your mind is Mr. Joyce is saying the slope of the tangent line, or Mr. Joyce is asking about the rate of change. Here, the slope of the tangent line is most appropriate to use. So do you think there are any problems with the slope of the tangent line? Sorry? Yes, but it's tangent at that point. The point where it is, it doesn't cross through. So yes, that's a good point. It will hit to more than one spot depending on the line. But for a tangent line, what might we have a problem with? So when I ask you, is there a problem with the derivative? If you're looking at the picture, you might be asking yourself, is there a problem with the tangent slope? So what do you think? Tony, what do you have for us? There's the line x equals 0. Do you see it? Is that tangent to the graph? It just skimming right across? That is going to be a problem because it's vertical, right? That's undefined slope. It's infinite. It doesn't exist. So if we were to do the limit process, we would come up with an infinitely steep slope. As I approach from the left side, going this way, let me just show you how we can do it visually. So as I approach, here's some tangent lines that you're thinking of, or should be starting to think of in your head. Done. So it's going like this as it gets closer, getting steeper and steeper and steeper. Then eventually it hits this vertical line, which what would we translate that to if we were looking at it? What is it hitting as it rises up? Not 0, because 0 would be like this. It's vertical slope, that would be infinite, right? There's no run here. The rise goes up, but the run it's division by 0. It's getting infinite. And what I was trying to show you here is it might be like 2, 10, 50. It keeps getting steeper and steeper until it's infinitely large, right? And then on the other side, the same thing is if I approach, right? This slope here, it's still positive. As I get closer, this one might be like 100, 20, 10. So as I'm getting closer, that slope is going bigger. It's infinite. So it's undefined because it's just infinitely large at the tangent line there. So it's undefined at x equals 0 because it's vertical. So what do we know about vertical asymptotes, i.e. it's a constant divided by 0? We would see that if we were to work the algebra through. Some constant divided by 0. So show me what you know about this. Let's talk about graph number 1. Where does the derivative fail to exist and why? What are you thinking of when I say derivative now? Hopefully it's oddly annoying that I keep asking this. Good, I'm hearing lots of slopes out there. So you're looking at a graph, but you're trying to picture the tangent slope at all those points. So where does that run into trouble? 0, there's trouble. That's right. So there'd be no derivative at x equals 0. The graph is not continuous there. There's a big jump. We can't do a tangent line through there. They're different, right? I've got that same problem where, like, where do you put the tangent line through? It's not defined, right? In fact, the graph itself is just a dot right there. So, you know, I don't know what to do with that tangent line. Okay, what else is a problem? Actually, you know what? Let's just say we'll forget that there are endpoints for now, but it would be very difficult to do the same thing. Like, what would you do? Let's not look at the endpoints, okay? We'll just look for problems in the graph itself. So we'll move on to the next one then. Where does it fail to exist? Yeah, what is the problem this time? Yeah, it's actually approaching infinity. So if you want to be real specific about it, eventually when it gets there, it's going to go like that, straight through it. It would be infinite, which is still undefined. So you're not going to be quizzed about like, oh, find the reason. It's basically it doesn't exist. The limit's not there. We can't find a derivative if the limit's not there. And the last graph here. What problems might there be for that last graph? There's a problem at 0 right here. Can you draw a tangent slope through there? And does it agree as you approach both sides? So like from this side, here's a tangent line, and it's approaching 0. And then from the other side, it'd be negative, but it keeps approaching the same thing as I get closer. They both approach 0. So in this case, there is no problem at x equals 0. Tablet's having troubles here. There is no problem at x equals 0. The derivative's nicely defined. It's right there. That's okay. All right, so if it's not at x equals 0, then what would we find a problem here? Yeah, there is a problem at 2, for sure, because if you try and put the tangent through, it's okay on one side, see? But on the other side, it doesn't agree. So you definitely don't have a derivative there. Anything else? Yeah, at -2, we see the same problem. Okay, so with endpoints and closed, we'd have problems there. Endpoints, that would be something like what we talked about here. If you have the endpoint of your graph, we're not going to look for the derivative at just that point because we don't have the other side of it to work with. The other things that we call a corner, for example, or a cusp, that's when you have a graph that goes something like this, right? It does that. Or maybe it's like a graph that goes like this. Generally, it's a piecewise graph, but there are some fairly crazy graphs out there who can do this without having to make a piecewise graph. But it's also a vertical tangent that can cause a problem. So that was like the cube root graph where we went through and you had this vertical tangent. Would also cause a problem. But essentially the same question is being asked is, can you draw the tangent slope through that point? And in most of those, well, in those cases you cannot, in the ones we've just been looking at. Okay, so what do you think? What kind of problem do you think is the tangent line has in this first one here? What's this? Yeah, a corner or a cusp would be, technically this one is a corner. A cusp would be one which, like this one here. But your terminology is just to help you at this point in picturing the problems that could go wrong. There's not going to be a terminology dependent question for you to answer. What about the next one here? Yeah, we've got a vertical tangent. That would also work on the last one. If you notice here, this tangent line's vertical. So we could also call it vertical tangent here. It's not defined when it goes vertical. All right, what do you think the problem is here? Yeah, there's a problem with the continuity. There's a jump here. Right, it's discontinuous. So if it's not continuous, it's not going to be differentiable. And then finally, this last one here is at a point or an endpoint. We're not able to find the derivative there. Now, there's a very important relationship between differentiation and continuity. It's one which you will certainly come across. And that's that if a function is differentiable at a point, and I'll call it C, then the function is also continuous at C. So usually the way you'll hear it said, so that you don't need to use all those words, is differentiable, differentiability. That'd be a good one for a spelling bee. Implies continuity. So I don't know if you noticed this when we practiced some of the advanced placement questions, but you might have noticed it said this graph is differentiable in the description. That's their way of telling you it's continuous without having to say it. So if something relied on continuity, like you're trying to use the intermediate value theorem, or you're trying to establish something about the graph that requires continuity, if you know it's differentiable, you also know at the same time it's continuous. So I'll show you the proof here. What we want is the limit as x goes to c of f of x to be equal to f of c, right? That's continuity. Now, then what I can also say is the limit as x goes to c of f of x minus f of c has got to be equal to 0. And then if I take that limit and I multiply and divide at the same time by x minus c, so on the top and the bottom, here's what happens. This is the limit as x goes to c of the first piece times the second piece. Now, I don't know what this value is here, but if I'm told that it's differentiable, this must exist. It must be a number that exists, otherwise there'd be no derivative. This is just the derivative at c. And this piece here, as x goes to c, that's going to be c minus c, which is 0. So c minus c is 0. A number times 0, that's not very exciting, is just going to be 0, which is what we said here would mean the same thing as continuity. So once you know it's differentiable, you must in fact have continuity. So I'm not going to, if you want to prove that this polynomial is continuous everywhere, what you'd have to show, I think I'll give us a break here, but all we'd have to show is that it's differentiable it's fast, why not? I'll torture you just another minute longer here. We'll take this definition, factor it, x minus c, x plus c, over x minus c. So I have the limit as x goes to c of x plus c. Now there is nowhere that 2c is not defined. You can use this derivative I've just found anywhere you want. So because I can use that derivative anywhere you want, that means it's differentiable everywhere, therefore continuous everywhere. So all I would do to finish off my proof is say 2c is continuous, sorry, is defined for all real numbers, and therefore x squared is differentiable everywhere and continuous everywhere. So we haven't done a lot of logic, but there is one thing you should also know from this. We've said it already, but it's something you can count on. If I tell you, for example, rain implies I will have an umbrella. Okay. If it's raining, what can you guarantee?
The water.
Let me say this one more time. Rain implies that Mr. Joyce has his umbrella. If it's raining, what can you guarantee? Mr. Joyce has an umbrella. Okay. Now, that's what we're saying here. Differentiable implies continuity. But there's another relationship. What else could you say about this? I come into school, and I have my umbrella. Oh, what do you know? You don't know anything. All the condition guarantees is if it's raining, I for sure have my umbrella. It doesn't say anything about I can't bring my umbrella to school on a sunny day, right? So implication only works in one direction. It doesn't work backwards. But there is a way to make it work backwards. What happens if I don't have an umbrella? It can't be raining, right? So no umbrella is no rain. So whenever you have one of those conditions, you have the other. So if differentiability implies continuity, what do you get for free once you've proven that? Not continuous. One more time. Not continuous means not differentiable. So there's no need to look for a derivative if you know it's not continuous. You won't have that.